Okay, so now we're going to talk about homology. So previously we had been talking about this idea of homotopy equivalence, and associated with homotopy equivalence is this idea of homotopy groups. But the problem is that it's hard to compute homotopy groups. So we're going to introduce this idea of homology instead, which is a weaker notion of equivalence between topological spaces, which is to say that it's not as able to distinguish between topological spaces, but it has the advantage that it is easier to compute. Okay, so far, right, we've been talking about well, I mean, it's like we had a sort of a sequence of sort of increasingly weaker notions of equivalence, where there was the idea of, it's like topologically equivalent in the sense of, homeomorphisms between spaces, right? Then we relaxed that to the idea of homotopy equivalence, and then now we're relaxing it further, okay? So we've been talking about sort of homotopy equivalence. But the problem is that homotopy groups are hard to compute. So we'll introduce the weaker notion of sort of homology. And intuitively, it's like one can think about homology as having to do with, the number of holes, if you will. It's like in a space, okay, of different dimensions, okay. And so I guess I should remark that if you have homotopy equivalence, right, then that implies that the homology groups are isomorphic, right? So homotopy equivalence induces sort of isomorphism on homology. But again, in general, it's like, homology, it's like is weaker in the sense that it's less able to distinguish between spaces. Okay. So this is sort of a trade-off, if you will, right? I mean, it's, at a computational level, it's like you're going to trade off things which have less ability, if you will. It's like to distinguish between spaces, but the advantage is that they're easier to compute. Okay, so let's go ahead and develop this further. And I should also say that sort of in anticipation of the fact that we're going to do what is called persistent homology, where we compute the homology not just of a single complex, but of all this sort of, one parameter families of complexes, where we talked about the alpha complexes and the, it's like the check complex and the Viatoris-Rips complex, where there's a parameter in there, all right? So in anticipation of that, we're actually going to do something in addition, where it's not just that we're going to compute homology, but we're going to compute homology with sort of z mod 2z coefficients. So basically 0 and 1. Okay, so we're going to take the coefficients and we're going to mod it by 2. Okay, so this turns out to make your life easier when you're computing persistent homology. It's less of an issue if you're just computing homology for a single complex. Okay, so this is sort of an anticipation of that. So let me sort of say a little bit about homology groups, right? So the basic idea is that homology groups sort of provide sort of a characterization, if you will, of the holes, if you will, in a topological space. Okay, and we're going to try to make precise it's like this notion of holes by first. So yeah, so perhaps the easiest way to think about this, if you will, is that we're going to try to describe holes by formal linear combinations of simplices, all right? And one way to sort of think about this is if you imagine that you have a loop on a manifold, right? You can try to approximate that loop by some formal combination of edges. It's like in a simplicial complex. All right, so that's going to motivate what are known as chain complexes. Okay, so let me say a little bit about chain complexes. So the basic idea is that let's say we have K, which is a simplicial complex. And sort of P is a dimension. Okay, so then this leads to the notion of a chain. So the P chains, right, are basically just some formal linear combination of p-dimensional simplices, right? Okay, so what I mean by that, so let's say the chain is C. I'm going to take some linear combination of alpha I, sigma I, okay, where sigma I are p simplices and not alpha, the AIs are coefficients. Okay, so normally when one, so this is a concept which shows up in a field called algebraic topology, and normally when one studies p-chains in algebraic topology, these coefficients are in the integers. Okay, and as I sort of alluded to earlier, in anticipation of the kind of algorithms we're going to develop for studying homology, not just for a single simplicial complex, but for this filtration of complexes which come from, it's like, things like alpha complexes. It's like where it is one parameter. It's like which is the radius, for example. We're going to make our life easier and consider the AIs to just be sort of modulo, sort of integers mod 2. Okay, so so for us, right, the AIs are going to be in what is called Z mod 2Z. Okay, so this is what is known as modulo 2 arithmetic. So what that basically means is that the coefficients are either going to be 0, 1, and then any multiple of 2 is identified with 0. Okay, so that's sort of the idea. And that's going to make our lives simpler. But again, it's like more generally, it's like these coefficients could be, it's like it could be integers, it could be reals, it could be rationals, it could be elements of a field or a ring. So there's a lot of possibilities. But again, we're just going to look at these coefficients which are in Z mod 2Z. Okay, so because of the fact that the coefficients are in Z mod 2Z, what ends up happening is that you can think of these p-chains as just being described by subsets of the p simplices, right? So because AI is in Z mod 2Z, right, we can consider, well, let me just say we can represent sort of a P chain with sort of Z mod 2Z coefficients as sort of subsets of the set of P simplices. And that's because when you have formal linear combinations of P simplices where the coefficients are either 0 or 1, obviously if it's 0 you just don't include it in the set, in the subset. If it's 1 you include the corresponding simplex in that subset. Right, so this is very, very natural representation. So this representation obviously only really works. Naturally, it's like when you have Z mod 2Z coefficients, if you have integers or stuff like that, then thinking of a P chain as subsets of the set of P simplices doesn't make sense. Okay, so this sort of representation only sort of makes sense with sort of Z mod 2Z coefficients. Okay, so all right. So the fundamental objects now it's like we're working with are these P chains. So we're going to define a few operations in them. One very natural operation is adding two P chains together, right? So let's say I have C, which is some AI sigma I, and D is BI sigma I, right? Then clearly C plus D is this chain, it's the sum of AI plus BI sigma I, right? So it's sort of, you basically just add the coefficients. And again, this is interpreted, it's like as an element of Z mod 2Z. So if, for example, you have a 1 here, I mean, if the coefficient is 1 in both cases, right, then you get 1 plus 1, which is 2, but 2 mod 2 is 0, so that sort of disappears. Okay, so previously we had talked about representing these chains, it's like with Z mod 2Z coefficients, as subsets of the set of P simplices. Okay, so if you go with that representation, right, you think of C as just being the set of simplices with non-zero coefficients, and the same thing here, then what happens is that at the level of sets, right, this sort of addition property leads to what is known as the symmetric difference. Okay, so sort of in the set representation of sort of P chains, right, the addition operation corresponds to what is known as the symmetric difference. So let me try to explain to you what this symmetric difference does. Okay. So there's sort of several ways to think about this. I should also say that if you're used to thinking about, it's like logical operations with sort of binary digits, for example, right, then this addition is basically the XOR operation, right? So addition, right, in Z mod 2Z, right, corresponds to sort of the XOR, exclusive OR operation in sort of logic gates, if you will. Right. So if you've seen logic gates before, it's like, and you've seen the exclusive OR operation, then that's sort of one way to think about it. I'm also going to think about it again in terms of this symmetric difference. So if I had a set A and a set B, I can introduce what is called the symmetric difference of A and B. So A delta B, Okay, so one way to do this is to say I'll take A excluding the set B, right, which is sort of this piece, okay, and then I union it with B excluding A, right, which is this part of it. Okay, so that's one way to express the symmetric difference. Another way to think about the symmetric difference is that it's the union of A and B, and then I exclude the intersection of A and B, right? So, so in that picture, it would be, this would be the union, right? A union B, and I have to exclude the intersection, which is just this piece. A intersect B, okay, which is of course just this thing here. All right. So again, it's easy to convince yourself that if you're trying to represent this chain as a set where you just look at the set of points with non-zero coefficients, and this is a set, then the set which represents C plus D, right, is exactly the symmetric difference of the sets representing C and D individually. Okay. All right. So now we have the objects of a set, right, which are the P chains. We have a operation which is addition. Okay. So so you're almost in a setting, it's like where you can talk about the group of P chains, right? So we still have a few more things we have to do, obviously, right? So if you have a group, you have to have a identity element, right? And you have to have an inverse, okay, to your operation, which is addition, okay? So let's see what we have so far. We have P chains, which are these formal combinations of P simplices, right? So AI is a Z mod 2Z in our case, and then sigma I is a P chain, a P simplex. Okay. Then we have the addition operation. Right. So sum of AI sigma I plus sum of BI sigma I is equal to the sum of AI plus BI sigma I. Okay, so so this is an example of what is called a group homomorphism. Okay, so in the sense that the addition operation actually, let me talk about that later. Okay. So, no, how should I say this? Well, yeah, okay. So let's say we have a bunch of coefficients. Let's say A0 to AM, for example, right? There's a map from that to sort of this formal linear combination, AI sigma I, right? So so here you have sort of Z mod 2Z to the M plus first power, and then here you have the P chains, okay? All right. So the basic idea, if you will, is that, you know, you can, by sort of constructing this notion of addition, it's like on P chains, you'll see that this map does the following thing, that if you have sort of Z mod 2Z, it's like to the M plus first power, right? That has, again, an additive structure. And if you do additions here, and then it's like take this map to P chains, that's equivalent to taking the two elements mapped to P chains and then taking the addition. Okay, so there's a sense in which this identification, or this map, it's like from coefficients, it's like to P chains, right, is a homomorphism. All right, okay, so this map is a, what is, we're going to call a group homomorphism, is a So, and what that means is that the sort of the natural operation, which is addition, right, which is the group operation, commutes with the map from coefficients to chains, if you will. Okay, and we'll see other examples of homomorphisms as we go on. We're not actually quite there yet, because I guess I haven't really actually showed that this set of p chains is actually even a group, right? So there's an addition operation. We still need to show that there's an identity element. Okay, so the identity element obviously is just this, the 0, so it's just this formal combination of 0 times sigma I. Okay, so clearly it's like that thing, if you were to add it to any chain, it's like doesn't change the chain. Okay, and there is also the inverse element. And the inverse of, so if you have C, which is this formal combination of AI sigma I, then the inverse, let's call that C inverse, right? It's just the sum of negative AI sigma I. Okay, but because of the fact that you are in Z mod 2Z coefficients, it turns out that the negative AI is equivalent to just AI. Okay, so this is equal to AI sigma I. So how do we see that? There are also only two possible values for AI. It's either 0, okay, so 0 and 0 inverse, 0 and minus 0 is of course equal to each other. And then the other possibility is 1, right? So 1 and minus 1 differ by 2. So in Z mod 2Z, in modulo 2 arithmetic, minus 1 and 1 are the same. So again, it's like minus AI corresponds to AI in Z mod 2Z, right? Okay, so in general, of course, that's not true. But if you have Z mod 2Z coefficients, that is true. So in any case, so now you have the elements. It's like of some set. You have introduced an addition operation. You can show that there's an identity element, and there is an inverse element to it. Okay, so these things together basically endow the set of p chains. It's like with a group structure, with an additive group structure. So, so the set of p chains, right, with the addition operation form a group, which we can call the group of p chains, and this is denoted by what we call CPK. Okay, so the chains of dimension p on the simplicial complex k. And then sometimes it's like we just say CP. It's like we suppress the fact that there's a complex associated with it. And if you wanted to be absolutely precise, we would normally say CP with the addition operation, right? But that's sort of usually understood, right? Okay, so so this sort of chain group, right, is abelian, right? So the chain group is abelian. Okay, which basically means that it's commutative, so it doesn't matter whether you add A to B or B to A, you get the same thing. Okay, all right. So these are going to be the fundamental objects. It's like we work with these chains. Okay, and then you know, we wanted to talk about holes, right? So one of the things we want to talk about then, so if you think about a hole as being sort of enclosed by, say, a closed loop, then we want to have some characterization of what it means for the loop to be closed. And one very natural way to think about that is to look at the boundary, right? So you can easily convince yourself that, you know, if you have something like a closed loop, or if you have the surface of the sphere, right, which again is like is something which encompasses maybe a hole at the center, of the sphere, right? These are things which have no boundary. Okay, so what's again very natural to talk about in terms of operations on chains is to talk about the boundary of a chain. And so this is what we're going to do next. So let me just stop for a minute.